Hello everyone. In this lecture, we will discuss on the relation between linear velocity and angular velocity for curvilinear motion. Next, we discuss on the components of acceleration, and at the last, we will solve some of the numerical based on curvilinear translation. So first we discuss on the relation between linear velocity and angular velocity. So let us consider a body is rotating on a circular path or on a curved path. So when it is moving on a curved path, so we assume the linear velocity of the body on the periphery is small v, that is written here, and the radius of the circular path that is defined in terms of small r, and the angular velocity of the body that is defined as omega. So here we consider this is the periphery of the circular path. So this is the linear distance that is covered by the body, and this is the angular distance that is measured by the body. So here we consider the relation between this v, omega and r. So we know that the length of the arc, so this is the arc of the total circular path. So we consider this length of the arc is equal to radius of arc into angle subtended in radian. So this length of the arc is measured as small v. So this v is what? The linear velocity, and this is the radius of the circular path that is considered as radius of arc here, that is r, into that is the angle subtended here. So angle subtended is omega. So what is the relation between this linear velocity and omega? Linear velocity and angular velocity, that is v equal to r into omega. So next we discuss about the acceleration. So when we discuss about the acceleration for curvilinear motion, so the linear acceleration has two components. One is the tangential acceleration and the second one is normal acceleration. So when we consider the tangential acceleration, it means that is the linear acceleration. So that linear acceleration acts along the periphery of the curved path, and normal acceleration is perpendicular to the curved path. So let us consider first tangential acceleration. When a body is moving in a circular motion, tangential acceleration increases the velocity of the moving body. So tangential acceleration is equal to dv by dt, that is change in velocity by with respect to time, change in velocity with respect to time. So this velocity is considered to be the linear velocity. So this linear velocity, we already defined the relation between linear velocity and the angular velocity, that is v equal to r omega. So in place of v, we substitute r omega. So r, that is the radius of the curved path, so that is constant. So we consider that to be constant here, and this becomes d omega by dt, and d omega by dt is what? That is expressed as alpha, that is angular acceleration. So the relation between this tangential acceleration and angular acceleration is that is equal to at is equal to r into alpha. So at is what? That is tangential acceleration. So next we discuss about the normal acceleration. So the normal component of the acceleration is known as normal acceleration, which is responsible for changing the direction of the moving body, and this is expressed as, that is normal acceleration is equal to v square by r. So v is what? That is linear velocity, and r is what? Radius of the curved path. So next we solve some of the numericals based on this curvilinear translation. So let's see the first question. A flywheel starts from rest and revolves with an acceleration of 0.5 radian per second square. What will be its angular velocity and angular displacement after 10 seconds? So, what are the given data? So, as it is considered the flywheel starts from rest, it means the initial angular velocity is considered to be 0. And the angular acceleration here it is given, that is 0.5 radian per second square. So, alpha is equal to 0.5 radian per second square. The time is given, that is 10 seconds. So what we have to find here? The angular velocity. What will be its angular velocity? It means it is the final angular velocity. So final angular velocity is considered to be omega, and angular displacement, that is theta. So we have to find out here theta and omega. So first we consider omega equal to omega naught plus alpha t. So omega is equal to, so in place of omega naught we substitute the value to be 0 plus alpha is given 0.5 and t is given 10 seconds. So after solving this, the omega is equal to 5 radian per second. So next we have to find out the angular displacement. So we use the another equation of motion, that is theta equal to omega naught t plus half alpha t square. So omega naught is equal to 0. So theta equal to, consider to be 0 into 10 plus half, alpha is 0.5 into 10 square. So this equation becomes theta equal to 25 radian. Right? So next question we consider here. A wheel of 1.2 meter diameter starts from rest and is accelerated at the rate of 0.8 radian per second square. Find the linear velocity of a point on its periphery after 5 seconds. So the diameter of the wheel is given 1.2 meter. So radius becomes half of the diameter, that is equal to 0.6 meter. So as the wheel starts from rest, it means the initial angular velocity is 0. Accelerated at the rate of 0.8 radian per second square, it means angular acceleration is given 0.8 radian per second square, and time is given 5 seconds. So we consider the equation of motion, that is omega equal to omega naught plus alpha t. So omega naught is 0. So we substitute that value, and omega is equal to 0.8 into 5. So omega equal to 4 radian per second. But here in the question it is asking that about the linear velocity. So linear velocity means we have to find out v. So v is equal to r omega. So that is the relation between the linear velocity and the angular velocity. So v equal to r omega. So the value of r is given, that is in form of diameter it is given. So we convert this diameter into radius, that is 0.6 meter. So we substitute the value here, and omega that we calculated right now, that is 4 radian per second. So 0.6 into 4 is equal to 2.4 meter per second. Thank you.